All right, so resuming to the time series model concept from the first part of the video, let's uh let's add to the AR model by adding both not only the autocorrelated, not only the dependent lagged based y variables, but also the explanatory time based variables. And so when a model has both y and x as their time based variables, we can call that the autoregressive distributed lag model. Short, we can call that short for ARDL. And so if you haven't realized by now, we can call just the AR model will only include the y lag variables, and then the distributed lag model will only include the explanatory lag variables. And notice how in the ARDL model the y the y starts out with a lag of 1, but the x variable doesn't do that. And the reason is because our output is actually the current y value. And so if we start out with the current y value in the right side of the function, that wouldn't intuitively make sense because we would have a direct autocorrelation. All right. So just a simple coefficient interpretation. Um, let's say given our DL model, we are given these coefficients here. Sorry for my cursor, it's lagging a little, but I got it. All right, so given this function here, we can say that the output increases by 4 when the current value of x goes up by 1, and that's what we call the impact multiplier, because we only consider the current or future values of the x. But let's say we advance the equation by one time period into the future. So all the t variables will be added by 1. And so now we have 2 as the current variable, but we have 4 into the future. And by the properties of the impact multiplier, we have what is called a cumulative effect, where we actually, if we're measuring the output of the future, then we also have to consider the current impact, which is in this case now 2, and the future impact being 4. And so we'll conclude that the cumulative effect based on the impact multiplier is these two current and future values added, that being 6. Okay. Just like heteroscedastic, or just like a linear regression and multiple regression model, we have assumptions for the time series model. So just like the previous two, we have a linearity. A little hard to interpret since these are time based, but all in all, they're kind of pretty much the same thing. Linearly related to the lags of the independent variable. So at the end of the day, we can still draw a linear line across a plane or a graph or whatever. We already mentioned that x and y need to be stationary, so it can't be moving significantly across the mean. Variance needs to be constant, and then the error needs to be independent of the current and path values. So no, yeah. So already went through this graphically, but pretty much no no correlation of the error and then the x. Error term is not autocorrelated, so errors can't be related to another. Again, pretty much similar to heteroscedasticity. And then the error term is homoscedastic, so it's constant. The third and fourth are kind of similar in a way, but it's still a little different because the errors. The third one is saying that errors can't show another pattern to another error, or we can't see a trend among the differences or errors, if that makes sense. Like our errors can't show a trend of each other. And then the fourth one is saying our errors can't, get bigger or smaller over time. They need to be relatively the same. Both graphically is very noticeable. I don't have one right now, but if you search up in like Google or something, it should be pretty clear. All right, now we get to the consequences of autocorrelation. So we have, how to detect for autocorrelation, what are the consequences, testing, and all that. So that's what I'm gonna do. Well, I'll cover in this video. And so similar to heteroscedasticity, we get that the coefficients are unbiased, so we can still utilize the coefficients given in our regression function, but it no longer minimizes the sum of squared errors, which in consequence we can't hypothesize tests or can't create confidence intervals. So detecting autocorrelation or testing for it, we went over the parallelogram. If it passes, based off the output of the software, if it passes the threshold of the autocorrelation graph, then we can conclude that it has autocorrelation. The second method is what we'll call the Lagrange multiplier test, often abbreviated as the LM test. And so similar to the BP test, the Begon-Prout, something like that, similar to the BP test for heteroscedasticity, we extract the residuals, use the auxiliary model to regress the errors on the other variables, and then we'll obtain the t-statistic of n times r squared based on the chi-squared. So yeah, pretty similar. And the Durbin-Watson test, which is pretty, from what I've seen, pretty much inferior to the Lagrange multiplier test, because the DW test only works for the first order autocorrelation of the errors. In other words, it only focuses on the linear aspect of the residuals. So when in doubt, use the LM test. The DW test probably has some benefits over the LM test, but if it does, it's not significant enough to know about it, because I'm sure that we didn't cover it. All right, so those are the three main methods to detect autocorrelation. How do we correct for it? First method, heteroscedasticity, again, also always similar. It's called the heteroscedasticity and autocorrelation consistent standard errors. We can call that the HAC. It extracts the residuals from the regression, calculates the variance, and then uses the weighted properties like we've covered before. However, this is actually different from the heteroscedasticity. The unique part of autocorrelation is we can actually add more explanatory variables, because adding the explanatory variables, it actually influences the recent values as well. So if the recent values are autocorrelated to the current output, and we add further past values, then you can actually alter the autocorrelation values of the recent values as well. But we can make the data longer, or the regression model longer and more expanded to potentially correct for autocorrelation. All right, lastly, we can try transforming the variables like logging or differentiating the data, differencing the data. So this is actually how we can also correct for stationarity or non-stationarity. So when we log or difference the data, we make the data in other ways, we make it less trendy, or less of more stationary, more random. And so what that'll do is it'll make it, because it'll make it more stationary, since logging in a way it shrinks the data, differencing makes it less less of a pattern, or less gives it a less clear trend. So that will reduce the chances of autocorrelation because that'll make the adjacent values less similar, and it'll also make the values more random to each other because there's less of a trend. All right. And so oftentimes when we're given models like regression functions like these, they're not going to be very, they might not be written in the neatest way. We have a time variable lag of 1 and then a lag of 3. This case isn't the most realistic because when we have a lag of 3, we should use a lag of 1 or lag of 2. But nevertheless, when we're notating in a short way, so AR, autoregressive, and the reason why I wrote 3 here is because we always look at the maximum, the oldest or the furthest time value first, or that's what we'll utilize or use to determine our notation. So even if the 2 is missing, we'll use a 3. For our ARDL model, because it includes the y variable of its past self, and then also an explanatory variable, we'll have like two notations here. So ARDL. Okay, this is actually wrong. That it should be 2, 4. So 2 y variables, 2 lag of the y, and then 4 lag of the x. So 2, 4. If we have like another explanatory time-based variable like a z, and if it's like a 3, then we'll write another 3 here. But yeah, you get the pattern. Always the highest lag order for each variable, despite it like maybe missing some lag variables like right here. Like intuitively, we should have a 1 and 3. All right, lastly, this is a little unrelated, but it's very important for future concepts. When we're regressing a model, not only just the time series models, but just regular OLS models, we don't always know if x is the impactor and y is the determined value. Y might have a bigger impact on x than x might have a bigger impact on y. And so the way we determine that is we'll use what we call the Granger test. So when we test for this, we try regressing y on x or x on y. Our null says, this regress function here, where x is a determiner, x does not affect y, whereas the alternative says it does. And so if the p-value is low in this type of test here, that means we reject the null saying x actually affects y, and we conclude that this function right here is valid. If it doesn't, then we'll have to try different methods. It doesn't necessarily mean y affects x because x affects y. We obviously have to consider other variables that are potentially have a big influence on either variables. All right, I'm going to leave it there at the time series models. In the next video, I'm going to go over endogeneity.